Space seems real. When you reach out your hand, you move through it. When you look up at the night sky, galaxies appear separated by vast distances. The entire architecture of our experience suggests that space is fundamental, that it exists as a kind of stage upon which the universe performs. But what if this is wrong? What if space itself is not a fundamental feature of reality, but rather something that emerges from deeper principles we're only beginning to understand? This question sits at the intersection of our most successful theories about the universe. On one side, we have general relativity, which tells us that space and time are woven together into a dynamic fabric that bends and warps in response to matter and energy. On the other, we have quantum mechanics, which describes the probabilistic behavior of particles and fields at the smallest scales. These two frameworks have proven extraordinarily successful in their respective domains, yet they speak fundamentally different languages about what reality is. And when we try to unite them to describe situations where both quantum effects and gravity matter, like the interior of black holes or the first moments after the Big Bang, our equations break down. This suggests we're missing something crucial about the nature of reality itself. The possibility that space is an illusion emerges from attempts to resolve this tension. Think about a familiar example from everyday life: temperature. When you feel warmth or cold, you're experiencing something that seems fundamental and real. But we now understand that temperature is not a basic feature of matter. Instead, it emerges from the average motion of countless atoms and molecules. The sensation of heat is real, but it's not fundamental. It's a statistical property that arises when you have many particles moving around. You can't point to a single atom and ask what its temperature is. That question doesn't quite make sense. Temperature only exists when you zoom out and look at the collective behavior of many particles. Could space be similar? Could the distances between objects, the three dimensions we move through, the entire geometric structure of the cosmos, be something that emerges from a deeper, non-spatial reality? This idea feels almost impossible to grasp because space is so intimately connected to our experience. We can imagine different arrangements of objects in space, different shapes and structures, but imagining the absence of space itself seems to require stepping outside the very framework of imagination. Yet mathematics allows us to explore territories that intuition cannot reach, and in those mathematical explorations, hints of a non-spatial foundation for reality keep appearing. One crucial insight comes from studying black holes. These objects are regions where gravity becomes so intense that not even light can escape. For decades, they posed a paradox. When something falls into a black hole, quantum mechanics suggests that the information about that object, every detail about its quantum state, should be preserved. Information in the quantum world cannot simply vanish. But general relativity suggests that once something crosses the event horizon of a black hole, it's gone from the outside universe forever, lost to the singularity inside. This creates a conflict. Quantum mechanics says information is preserved. General relativity says it's destroyed. The resolution to this paradox required rethinking what happens at a black hole's boundary. It turns out that all the information about everything that falls into a black hole can be encoded on its surface, on the two-dimensional event horizon, rather than in the three-dimensional volume inside. This is deeply strange. Imagine taking everything in a room, every object, every particle of air, every photon of light, and somehow encoding all of that information on the walls. Not by painting pictures on the walls, but by fundamentally representing the three-dimensional reality as a two-dimensional structure. This principle, where a volume of space can be completely described by information on its boundary, suggests that the dimension we think of as depth might not be as fundamental as it appears. This idea extends far beyond black holes. There are mathematical frameworks where an entire universe with gravity operating in some number of dimensions can be exactly equivalent to a quantum theory without gravity operating in one fewer dimension. The quantum theory lives on the boundary of the gravitational space, like a hologram encoding three-dimensional information on a two-dimensional surface. In these frameworks, space itself, at least one dimension of it, emerges from the quantum entanglement and interactions described by the boundary theory. The geometry, the distances, the very fabric of space in the interior are not fundamental. They arise from quantum information processing on the boundary. This suggests a profound shift in how we think about reality. Instead of starting with space and time as the fundamental stage and then placing quantum fields and particles on that stage, we might need to start with quantum information, with abstract relationships between quantum bits of data, and recognize that space emerges from the pattern of correlations and entanglement between those bits. Space would be real in the same way temperature is real, genuinely experienced and measurable, but not fundamental to the deepest description of nature. Entanglement provides a concrete way to think about this. When two particles are quantum mechanically entangled, measuring one instantaneously affects what you'll find when you measure the other, no matter how far apart they are in space. Einstein famously called this spooky action at a distance because it seemed to violate the principle that nothing can travel faster than light. But entanglement doesn't allow you to send information faster than light, so it doesn't contradict relativity. What it does suggest is that quantum correlations are more fundamental than spatial separation. Two particles can be maximally entangled, maximally connected in the quantum sense, even when they're on opposite sides of the galaxy. Now imagine building up space from entanglement. If particles are highly entangled, we might say they're close together. If they're barely entangled, they're far apart. The geometric structure of space, the fact that some things are near and others are distant, could emerge from the pattern of quantum entanglement in the underlying non-spatial reality. In this view, space is not the container within which entanglement happens. Entanglement is the fundamental relationship from which the appearance of space is constructed. This has strange implications. If space emerges from entanglement, then the properties of space should depend on the quantum state of the underlying theory. Change the pattern of entanglement, and you change the geometry. In fact, there are calculations suggesting that the smooth, continuous space we experience is what emerges when quantum systems are in highly entangled states. If you could somehow disentangle those systems, space itself would fall apart, losing its coherence. The connections between distant points would dissolve because those connections are made of entanglement. This perspective also sheds light on the nature of gravity. In general relativity, gravity is the curvature of space-time. Massive objects bend the fabric of space and time around them, and other objects move along the curves in that fabric. We experience this as gravitational attraction. But if space itself emerges from quantum entanglement, then gravity might not be a fundamental force in the usual sense. Instead, it might be an entropic force, a consequence of the statistical behavior of the underlying quantum information, similar to how pressure in a gas emerges from countless molecular collisions without being a fundamental force acting on individual molecules. Think of it this way. When you compress a spring, you're storing energy that the spring wants to release to increase its entropy, to move toward a more disordered state. The spring pushes back not because of a fundamental force, but because of the statistical tendency of systems to maximize their entropy. Some researchers have suggested that gravity might work similarly. When mass distorts space, it's actually changing the entanglement structure of the underlying quantum information. The attraction we call gravity could be the universe's tendency to reorganize that information toward a more probable higher entropy configuration. Space and time curve in just the right way to maximize the quantum entropy of the underlying degrees of freedom. This is speculative, and there's vigorous debate about whether gravity is truly emergent in this sense. But the very fact that such ideas can be formulated mathematically and connected to observations suggests we're glimpsing something important about the nature of reality. Space might not be what it seems. The implications reach into the nature of time as well. In our everyday experience, time flows forward. Events happen in sequence. Causes precede effects. But at the fundamental level of our best theories, particularly in general relativity, time is just another dimension, similar in many ways to space. The equations don't distinguish past from future in the same way we do. The arrow of time, the fact that we remember the past but not the future, that eggs break but don't spontaneously reassemble, seems to be a consequence of entropy and the particular state of the early universe, not a fundamental feature of temporal geometry itself. If space can emerge from non-spatial quantum information, perhaps time can too. Maybe at the deepest level, there is no time, no sequence of moments, just a timeless quantum state containing all the correlations that, when viewed from within, give rise to the appearance of temporal flow. This is even harder to wrap our minds around than emergent space, because our entire mode of thinking is temporal. We reason in terms of before and after, cause and effect. A reality without time seems not just foreign, but incomprehensible, yet the mathematics of certain quantum theories suggest this might be closer to the truth than the familiar flow of moments. What would it mean for space and time to be emergent rather than fundamental? For one thing, it would mean that the very questions we ask about the beginning of the universe might be ill-posed. We often ask what happened before the Big Bang, but if time itself emerges from a deeper quantum reality, then there might not be a before in any meaningful sense. The Big Bang might represent the boundary of the emergent space-time, the point at which our familiar notions of space and time begin to apply, but beyond which those concepts simply don't make sense, like asking what's north of the North Pole. It would also transform how we think about the unification of physics. For a century, physicists have sought a theory of quantum gravity, a framework that would unite general relativity and quantum mechanics into a single coherent picture. Most approaches have tried to quantize gravity, to make gravitational fields behave quantum mechanically while preserving the fundamental nature of space-time. But if space-time is emergent, the challenge shifts. We don't need to quantize gravity, we need to understand how space-time and gravity emerge from a more fundamental quantum theory that doesn't reference space or time at all. Several research programs are pursuing this vision in different ways. Some involve theories where fundamental objects are not particles, but tiny loops or strings existing in a higher dimensional abstract space. Others involve networks of quantum information, where nodes and links replace points and distances. Still others focus on reformulating known physics in terms of quantum entanglement and information theory, finding new principles that might point toward the emergent nature of space-time. What unites these approaches is the recognition that our intuitive picture of reality, with its solid three-dimensional space and one-dimensional time, might be a kind of approximation that works beautifully at human scales, but breaks down when we probe the extremes of the very small, the very massive, or the very early universe. This raises a philosophical question that has echoed through the history of thought. What is real? We've learned repeatedly that our senses and intuitions can mislead us about the nature of reality. The Earth seems flat, but is round. Solid objects seem continuous, but are mostly empty space with tiny nuclei and electron clouds. Time seems absolute, but is relative, flowing at different rates depending on gravity and motion. Each discovery has required us to revise our concept of what exists fundamentally versus what emerges or appears from a different underlying reality. The possibility that space is an illusion represents perhaps the most radical revision yet, because space is so basic to our conceptual framework. We organize all of our experiences spatially. Objects are located in space, events happen in space, we move through space. The idea that this might be a kind of cognitive and perceptual construct, real in our experience but not fundamental to the universe itself, challenges the foundation of how we understand existence. Yet there's a comfort in this too. The history of physics is a history of discovering that reality is stranger, richer, and more subtle than it first appears. Each revelation has opened new questions and new possibilities. If space emerges from quantum entanglement, then understanding that emergence could unlock new insights into the nature of consciousness, of observation, of the relationship between the abstract mathematics we use to describe reality and the reality itself. It might help us understand why the universe seems so finely tuned for complexity and structure to arise, why the laws of physics have the particular form they do, and what, if anything, existed before the Big Bang. We should be humble in the face of these questions. The idea that space might be emergent is not proven, and even if true, the details of how it emerges remain deeply mysterious. But the pursuit of this idea reflects something essential about the scientific endeavor: the willingness to question even the most basic assumptions, to follow the mathematics and the evidence wherever they lead, and to recognize that the universe is under no obligation to conform to our intuitions. When you look around the room you're in, you see objects separated by distances. That perception is real and reliable for navigating your world. But at a deeper level, those distances might be manifestations of quantum correlations in an underlying reality that has no spatial structure at all. The space between you and the wall might be as emergent as the warmth of the air, a higher-level description that arises from microscopic quantum relationships that are more fundamental than geometry itself. Space might be real in the way a rainbow is real, genuinely there, observable and measurable, but not fundamental, not an object in itself, but a phenomenon that appears when deeper structures interact in particular ways. This perspective invites a sense of wonder. We are creatures who emerged from the universe trying to understand the universe. Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, and yet we've developed mathematics and experimental methods that allow us to probe far beyond those everyday scales. That we can even conceive of questioning the reality of space itself is remarkable. That we can construct mathematical frameworks where such questions have precise meanings and testable consequences is more remarkable still. The universe may be far stranger than space and time and matter. It may be at its heart a quantum informational structure, a web of entangled relationships and probabilities from which space and time and the appearance of solid matter emerge like patterns in a complex tapestry. We are part of that tapestry, woven from the same fundamental threads, and yet we can step back and examine the weaving. We can ask what we are made of, what space is made of, whether space is made of anything at all, or whether it's an emergent phenomenon like temperature or pressure or life itself. These questions push us to the edge of understanding. They require new ways of thinking, new mathematical tools, new experimental approaches. But they also connect to ancient questions about the nature of reality, the relationship between appearance and essence, the limits of human knowledge. In questioning whether space is fundamental, we're continuing a conversation that has been happening for thousands of years, using the newest tools of mathematics and physics to probe questions that philosophers and mystics and scientists have wondered about across cultures and centuries. The answers, when they come, may not be final. They may open yet deeper questions. But the asking itself, the careful, rigorous, imaginative asking, is how we expand the boundaries of human understanding and glimpse the profound strangeness and beauty of the reality we inhabit.